Alright, in this video I'm going to show you how to actually sketch a path and image of that path under a complex function, not just several dots. So first I typed in the complex function like this, function f, that's the name of the function. The variable appears like this. In Mathematica, to define it as a function, there's underscore and exponential z, so it's a complex function. So here's the path I typed in, so I call this a z path. That's going to be the real valued function. T here is going to be the real. And of course, if you accidentally type in a complex number, it'll calculate the complex number. So in our mind, we know it's a t. So this I is the center, and minus, I'm going to change that to positive. Positive to exponential t. So I is fixed, and that's the central point, and that's the circle. So you know I is kind of shifting. So this is a circle, exponential ti. Shifted, the centers are shifted to I. So that's what this is representing as t goes through 0 to 2 pi. And after that point, it's going to be repeating. This part I'm doing in here is just the technical part. If you go back, this is giving the size of this window, or the size of the domain. From left hand x coordinate and y coordinate, this is a lower y coordinate and upper y coordinate. So this 5 being 10 by 10 image and 10 by 10 domain, and we're going to be looking at. So I need that to make it prettier at the end, so I put it here at this stage. So that's what this is about. It's not a special command, it's just a bunch of number, and then I'm going to use it in part of more complicated commands so that I don't have to type this one back and again and again. So another thing I'm typing in here, this is actual complex value that, as far as I know, doesn't seem like the Mathematica actually sketch this complex numbers as we hope it to do. But we're going to use this xy coordinate system. So here's a complex number, whatever that is. We want to turn that into an xy coordinate system. We do this a lot. So I made it into a command. If I give a complex number z, this convergent to xy will take the real part and an imaginary part and turn it into a position vector in xy plane. So we use this a lot. Instead of typing this, we just use convergent xy, and it does it automatically. Right, next thing I'm showing here, this is the input, the value of complex, and we're going to stick that one into the complex value function so that we get an output. So here's an input value going into the function. That whole thing is going to be the output complex value. So I named it image path, but t is still the variable and the real variable that goes and controls this z value in a certain, parameterize a certain z value in a one complex plane. So input value is represented in terms of t like that. Here now I'm turning these complex numbers, z path, the input complex number, and image path, this image complex number, turning into an xy coordinate system. So now z path xy, image path xy is representing xy coordinate. So you can use that to plot all those different points as t virtually varying continuously. I realized I didn't have a and b specified here, so a and b is given 0 to 2 pi, the circle around I, and that's what it's going to plot. So I'm going to run this and show you what that fig 1 looked like, and that's a circle there. Okay. When you plot this later, and we're going to use this box condition so that we're going to fit this large circle into that 10 by 10 unit box, so it's going to look smaller. Right now, that itself is just one graphic element defined as a fig 1. So if you do it also like this a and b, later if you want to change the beginning and end point, all you have to change is just that one line. Everything else will change automatically. So this is a good way to do it. So defining several constants at the same time in one line is this way. It's a way to do it. Otherwise, you have to do it a equals and b equals on a separate line. So this is a convenient way of doing it. To that circle picture, I wanted to add one more thing so that we know where it starts and where it ends. So I decided to plot the terminal points. This is a point x comma y, and it begins here, ends there. So this one is the point, the terminal points, because it's a terminal parameter value. But list plot requires list of points. It itself is a point, but it has to be in a list. So the list of a point, even though if there's one point. Now this is determining the size of the dot. So we're going to put this into on the same picture. I don't know how to define that as a one graphic element, but if you put in a brace like this, later when you use the show command, it's going to show an overlaying it all together. So that z-path dot will be that circle with a terminal point with this mark indicated with a dot in this fig 2. The next thing we're going to do is we're going to sketch this image path. So here, instead of the z path, we have image path already defined in terms of t. So you plot those. Now I'm plotting in a slightly different color so that I can, of course, it's separated, but it's easily distinguished as red color. And now I'm doing this plot range here. It's a showbox. Plot range is supposed to have this structure, x min and x max and y min and y max in there. Rather than typing this one over and over, I just define it like this, so it's a convenient way of doing that. And also I wanted to plot the terminal point in there, so I do the same thing in here. Right, it is. Fig 4 is going to be a point of this image path, the last terminal point with red color and the sides. So fig 3 and fig 4 is the image path and the terminal point indicated. And I'm defining the whole thing together as image path dot. So here, first I'm showing you that the z path, the path in the domain with a dot at the end, and image path with a dot at the end. So that's what that is. So if you run the whole thing, it's supposed to give you the two pictures. Now you can see I'm putting this plot range show box. So I'm showing this circle and its image in this show box size, which is where it is, a -5 to 5, -5 to 5 size of the window. Alright, it's showing the first picture is shown in here, and that's the beginning. A terminal point is started here and circle around, and that's the center I. So under the function, which is exponential and complex, it goes to that shape. It's a weird thing is going on there, but that's where it starts and where it ended. And for these nice functions in whole complex numbers, this orientation of rotation never changes. So it's still rotating around counterclockwise. So the visualizing these two results vertically like this is kind of difficult to see. So the Mathematica has a command to grid these graphic elements and put into a nice grid. So grid is a 2x2 or two-dimensional arrangement. So you have to write it just like a determinant. So I'm going to share this. It's a grid, go like this, and inside the grid, the entire thing is a list, and the first one here is going to be the first row, and that's going to be the second row, just like the matrix. If the first row has 2 elements and 1, 2, and second row has 3, 4, you can imagine this is a matrix of 1, 2, 3, 4. But we're putting these graphic elements in here and organize it slightly better than vertical arrangement. So I'm going to put that show command into the first row. I think I did it wrong. So copy, and the first row there is copied. And the second element in the first row, that's this spot in here. I'm going to do the same thing. And then I'm not going to have a second row. In that case, it's going to have just one row. And there's this double braces because of one row thing. If I get rid of that, and it gives you slightly better arrangement. It's going from here to there. Okay. So this is a good example of showing you on how to change this entire sequence of commands into the one command. So if you want to look at a different circle, for example, if I shift it to slightly to the left, just like -1, -1 plus, then it's going to be the same size of the circle and centered in a different way. If you run the whole thing, now you can see the circle is shifted left a little bit, and this image is slightly different. So suppose you want to repeat this over and over again, and what you're doing here is always the same, so you keep hitting the shift enter all the time. Rather than doing it like that, you can, these information in here is completely determines what comes rest of the part. So we can kind of name this procedure to something. So that's what I'm about to do. So that's kind of the same. This is the same setup, and seems like from here, the rest of the part is exactly what we do all the time. So from here is going to be a procedure. So I'm going to name the procedure to be sketch image maybe, and you put input data first. We have to give the complex function f, so you don't have to type in the formula. You in advance define that complex function with a certain name like this, and you just call the name, but you gotta have this underscore there. And next thing is also the name of this path we defined, not the formula again. You don't type in this formula into that place, just the name, and it's a better way to handle this. Another thing is that I decided to also change this A and B so that you can see, by changing this one later, but let's not make it complicated. I'm just going to fix it to A and B always 0 to 2 pi. I'm just going to look at the circle, and it seems like that is it. That's the only command you need. And then you close it, and it's the symbol, and go to the next line. And this is a good idea to put this module command and declare all the local variables so that you don't get confused with the variable you use here and outside this procedural command. So you go through entire command and declare all this thing. Conversion xy, that's going to be the local command inside. Image path is going to be the local command inside, and so on. This is a built-in command, so you don't have to do that. So I'm going to list them all. Alright, I think I list them all. As I list within this parentheses, Mathematica automatically change the coloring of this local command in here, and it takes care of it. So I don't think I close that module bracket. I go down there. If I close it, it recognizes close it. So now it's the procedure sketch image is defined. So rather than you keep hitting enter all the time, you can just copy and paste this setting right there underneath it. Now we have this much of the setting, and you want to sketch the image of this one. Function is this, and z path is the path for the input value z, and that's the window size. And then what you want to do is a sketch image of this complex function without, when you actually use the sketch command, you don't need the underscore. That's just a z path, and then it's going to sketch it for you. So now, if you want to change a little bit, maybe you want to sketch in a slightly different way, maybe along the real line, maybe 3 there, then it's going to switch to 3. I think its image is outside the box. So if you want to see the bigger box like a 10, maybe it's out there. It got really big as I put it out there. So if I switch it back to like 1, you can see it's all in there, things like that. And of course you can keep hitting shift enter in here. There's a lot better way to kind of organize things here. Now with this much of now it's shrunk down to the 5 line, you see how the things are exactly going on the structure. You want to vary more. For example, what if I change the radius of the circle, not just that one? So if I throw in, alright, here 0.5, and I see the picture, I want to see on the next shape maybe 0.7 and things like that. So if you want to change that part and keep repeating this one, this whole thing is again repeated over and over with this parameter 1 parameter. So you can go back and you do the following thing. This is going to be the radius r. I'm going to keep changing, and then this entire 5 line is repeated over and over just like that, and I'm going to call it vary radius. The entire procedure of changing just that r part is named now. Here's input values r underscore, and module again. It's a good idea always to put this thing, and then list things here. I don't think it's necessary to define, well, I'll just do it in here like this. F and z path, these are all can be considered as a local variable, and maybe I'll just just keep it this way, B, and I think it is small. You can check the color and see how it if I covered every local variable there. If I close it, now you have now named entire procedure again. So if you, all right, I wanted to vary the radius to 1.2, and that's that. If you just want to change to 0.3, and it's going to do it quickly. Now the entire long lengthy procedure is all have one command to vary radius, and you can see it here. So the power of naming the procedure and again and get down to this level is that you have a better control. I'm going to show you how to animate this one. Now you want to change this as R, and you want to show the animation. So that's the animation command is manipulate. So there. So if I change R continuously, I want to show how the domain looks like and how this thing changes. So R varies from maybe 0 to, I'm going to show you 0.5 to 2.5, maybe 2. If you do that, it's going to show you animation interface, so that if this is a 0.5 and this is 2, so if you continuously change R value, you can see that this image is keeping the domain keeping the circle shape, and its image is continuously changing to some of this type of a shape. Okay, so think about it. This long organized way of thinking is called into a procedure with this name, and later you can just simply call it like this and see the whole picture in a very nice way like this. Alright, at this stage, let me show you another possibility. It's after you organize like this, it's quite easy to change things in here. Alright, what if I change that to z squared minus z, and then it's a new complex function, and the radius changes in a slightly different fashion. You can see that something's going on down there. So that's the power of using this procedural command to do things more effectively and investigate in a whole lot better way. One last thing is that if you write it like this, and its initial value is always set to 0.5, but for some reason, from my experience, it's good to have this initial control. If you want, after you run this cell, if you want R, it's set to be certain values such as 1, and then you put this around like this, and then it's going to set it to the initial value 1, and then you can go from there and back and forth and see this animation. That's all I have for now, and I hope it helped you to further investigate in more efficient way with Mathematica. Bye.